So let's say a little bit more about this counterfactual world. I forgot to use the laser pointer. Something about the risk-based approach, which relies on comparing a counterfactual world to the current world, but this is often also done by taking a period, let's say in the model simulation or reanalysis from a period few decades ago where the human influence is considered minimal, but this is not as clean as trying to create a counterfactual world, but then creating a counterfactual world requires certain assumptions as well. Just in terms of impacts, we already talked about attribution, but here it can be climate attribution or impact attribution. So we would look for affected quantity being climate change or climate impact, and the drivers being anthropogenic climate forcing that we talked about and we will talk about, and the causative agent being climate change and the affected quantity being climate impact. So these attributions can be different. For example, for hurricanes, people look at impacts that is not just climate change but also how people have moved closer to the coast and so on. So you have to separate the impact of just climate change on cyclones and cyclone impacts on life and property and infrastructure versus how people have gotten in the way of hurricanes more or cyclones more by moving closer to the coast and so on and so forth. So that's just a point. But in terms of factual and counterfactual, the easiest way to try to create a counterfactual world is to take a coupled model and prescribe carbon dioxide levels from the pre-industrial level of, let's say, 280 ppm, which has then since then increased to over 400 or so, 420 I think by now. And you also include the other forcings, radiative forcings of the time, like volcanoes and solar physics changes in sunspots, etc. So you create a period which is clearly not seriously affected by human activity, like the pre-industrial level, which can serve as a good counterfactual climate. Of course, that had natural variability, like medieval warming and little ice age and so on. So all these questions remain. One can also try to do these by using forced sea surface temperature forced atmospheric simulations, which are much faster, allow you to make multiple realizations and so on, produce what are called large ensembles by perturbed initial conditions, where you can get better statistics of the extreme events and so on. But then creating sea surface temperatures for the counterfactual world becomes an issue. People take warming patterns from the observations or models and subtract them from the current available sea surface temperatures to produce past sea surface temperatures to force the atmosphere to produce counterfactual climate and so on. So it's not a simple business at all, but here is a good example of how it is done nonetheless. Here we are looking at near surface air temperature in Kelvin for a particular year, 2016. This is at a particular grid point in the Mediterranean region at 43.25 north and 5.25 east. So just go up West Africa into the Mediterranean region. And it is showing the factual and counterfactual temperature seasonal cycles at that location. So here mu A is the factual, so it should be counterfactual, sorry, factual CDF. So you have T is the global mean temperature and how it has changed over this time T, to which you have gone back in terms of counterfactual temperatures. So you can see that the counterfactual temperature is lower. This is the expected value, by the way. Mu A and mu B are the expected values. And so you can see the ranges over here of when you pick a particular year, you get large ranges, of course, in terms of internal variability that is related to everything that affects the Mediterranean climate: NAO, PDO, ENSO, Atlantic Nino, and so on and so forth. But nonetheless, you can see that the factual temperature is clearly higher, and then you compute the cumulative distribution functions for a particular day here on October 25th of 2016, for which you are trying to do the attribution, and then you are looking at cumulative probabilities and how they changed for a particular range of temperatures going from there to there or there to there, and you can see how the factual cumulative distribution function and counterfactual cumulative distribution functions for October 25th are changed by the human activities and global warming. Okay, so that's a quick example of how it is done. In the end, the results look like this. So this is likelihood of a particular event, and this is a variable which looks like this in terms of distribution in the counterfactual world with the mean and the tails, whereas the climate variable that you are looking at in the actual world has changed this way, and you are typically looking for a threshold of extreme. So either on this end, let's say warmest temperatures or coldest temperatures, so 95th, 99th percentile types or 1 percentile types, and so on. And you can see here how the likelihood has changed in the counterfactual world being P0, and in the actual world having jumped to P1. Okay, so this is the idea of the risk based approach of attribution. Lots of details there. The so-called Boulder approach goes the other way, where it takes models, takes a particular event. So here are observed June to August 2011 temperatures. It has this kind of a pattern which has certain PDO phasing, let's say, or you can also think of it as, maybe I shouldn't get into the details of that sort, but this pattern here has an impact on precipitation or Texas here. So this is a serious drought here, and the percent of climatology was excess here and here. So if you want to focus on the event here, so you observed SST anomalies on the left, and US precipitation anomalies for contemporaneous conditions for June and August 2011. And in these are the antecedent conditions for October 2010 to May 2011. So you can see that there is a La Nina pattern here, even though the maximum is shifted away from the coast here, and it has this kind of a pattern that has science behind it, like Rossby waves and so on. And you can see how the observed precipitation changed from the antecedent conditions of June to August 2011 to October to May 2011. So, okay, all anomalies are relative to an observed 1981 to 2010 climatologies. So what is the point? The point is that the Boulder approach does simulations, tries to find climate drivers that can explain a particular event, and then you can see whether the temperature anomalies here, temperature trends here, have any impact. So it's not looking for altered probabilities as in the risk approach, but it takes the approach of explaining the drivers and then looking at those particular drivers. How are these patterns changing, how are these temperatures changing, and how they would change the events in precipitation observed here in terms of a drought over a certain part of the US. You can do this for any part of the world. There is also what is called analog pattern or narrative approach, where you take a certain event, you look at the circulation pattern, and you go back and find analogs in the past and see how a similar pattern in the past would have produced a drought here, and how a current pattern of a similar nature has produced a drought, and you try to compare the two events. So obviously the questions answered by the risk approach and the Boulder approach are very different, but nonetheless both are trying to do attribution of an event that is detected in observations. So we will see next on how the framing of the questions themselves begins to answer different questions, and the main thing to keep in mind is that the attribution science itself is important, and it's probably important to develop a unified approach. But in the meantime, the idea of doing attribution doesn't necessarily translate into action. People like to hear when a big heat wave happened in the Northwest and temperatures were beyond anything a generation or two had experienced, then saying that this was greatly exacerbated by global warming makes people understand that this is what global warming does. So there is a value to it. But does this mean it helps in mitigating it or adapting to it? Maybe, because if you say the frequency of such events are going to increase, then there are responses that can be triggered at various levels of governance and policies and resources and so on. Okay?